All right. Hi, everyone. Um, Welcome to online metaprogramming. Um, this is going to be a little weird. I'm going to have to get used to this. But I think the class will be totally fine online because I've just got slides, nothing really in person. I can point out things with my mouse, and people can still ask questions. So if you have a question and you want to ask it, just unmute yourself and just go ahead and ask it. I know there's a feature to like raise your hand in the chat. Not gonna lie, I'm not gonna notice that. So go ahead and unmute yourself and interrupt me because there's no way I'll notice it otherwise. Also, if you have a camera and are, not totally unpresentable, feel free to turn on your camera because, we're all friends here. And it's good for me to be able to gauge how you guys are reacting to the material. So if I'm seeing a lot of this, then I can like slow down. And that's something that, I do in person, but without being in person, every camera that's on is, helpful feedback for me. Yeah. So as far as course logistics go, pretty much the same as before, just everything is pushed back a week. So that includes the homework assignments. So there was going to be a homework due today. That's now due a week from today. Rashid has set his background photo to a picture of me from like high school. And I can hear Josh laughing from the other room. Josh, you can mute yourself, but you're just right back there, so I can still hear you. You can't mute yourself. All right. Well, that's going to be distracting, but okay.
I'll try to keep quiet.
So everything's just pushed back a week. Yeah, all the topics should still be on, unless there's some topics that I still haven't written the slides for. We'll see how my motivation is doing on those. But for the topics that I actually have a start on or like have entire slide sets for, those will be on. So yeah, hope you guys will enjoy the rest of the class. Today, we're going to talk about attribute access. Let's see. Which means we're spending basically an entire course on the dot, just what exactly happens when you use a dot in Python. So let's get into it. First of all, are there any questions about logistics or homework or how this class is doing? Thoughts, comments, questions? All right, cool. Let's get into it. So like I said, we're spending an entire lecture on dot and what dot does. It turns out dot is a pretty complicated operator, especially in Python. But Python, being super meta, gives you access to the dot. And you can, modify what happens when you use a dot. And that ends up being very meta because we usually think of a dot as just a simple lookup. You have some object and you want a field and you use a dot to get the field of the object. That's what we think is happening, but we can change that, which allows us to implement kind of modifications of what we consider usually program structure. So let's get into it. Oh wait, that doesn't work. Okay. All right. So in order to talk about the dot, I'm going to make a class. But instead of defining an init method like we usually do, I'm just going to define some variables right there in the class. And this is not what we usually do. Usually we, write an init method, and then when we want to declare fields of a class, we set them to self. So init takes in self, and then it takes in some maybe parameters, and it sets self dot. We would say like self dot integer equals 1, self dot mylist equals empty list. And that would assign those fields to the specific instance. But that's not what we're doing here. This is more similar to how you might see a class in Java. We're just declaring these right there in the class body. And some of you guys actually did this for some of the earlier assignments. And it's actually not so obvious what is actually happening when you do that. So here we're just going to investigate. We're just going to declare these fields and see what happens when we try accessing them with a dot. So first off, if we say foo.integer, what would we probably expect? I mean, there's no self in this definition here. We haven't assigned these to anything except just the body of this class. There's nothing else that these fields could be associated with, really. So we would expect foo.integer to be 1, and it is. So not too shocking. Foo.mylist, similarly, empty list. And if we call foo.foo on 2, and foo here, the lowercase foo is a lambda expression, so that means it's callable. We can call that function. And it takes in 1 parameter and returns that parameter. If we call foo.foo on 2, what do we expect? Well, this kind of looks like a method call, but we're calling it on the class itself, which means this is actually a static method call. So there's nothing weird going on here. This is just a lambda expression that we're accessing through foo, and we get 2 back. All right, so we also covered this briefly in the first lecture, the dunder-dict attribute. And it had to do with the things that we could access on that object through dot. So it was a while ago, but I think we took a list and we looked at the dunder-dict of a list, and we saw like append and insert and delete, a bunch of, as strings, we saw the names of methods that we could call on a list. So here, what do we expect to see on foo? Well, you can kind of see it visually. This class body, we've just made a bunch of definitions. This kind of looks like a dictionary. You could easily imagine refactoring this little code snippet to be like a curly bracket, some quotes here, colon, and you could turn this into a dictionary. It turns out that's exactly what's happening when you write a class in Python. The class body turns into a dictionary of those definitions. So if we look at the dunder-dict of foo, we get a dictionary of everything that we put in foo. We got integer, mylist, and foo as a lambda expression. Questions about that?
I have a question about why, if we did like foo.integer, we get 1. Why, like, if we also did foo and then we like called an instance of the class .integer, we also get 1.
Great question. Great question. So that's exactly what I'm about to get to here. We're going to call the class and we're going to make some instances, f1 and f2. And if we look at f1.integer, yeah, like you just said, we actually get 1, which is not what we might have as expected, because there's no self here. Like this class definition, we didn't write any methods, we didn't take in self, we just associated these things with foo. But now we have some instance of foo. How does it know about integer? Well, let's see. If we change f2.integer to 4, so look, before we were looking at f1.integer, now we're looking at f2.integer, and we're setting it to 4. Then we print out f2.integer. What do you guys expect? I guess since everybody's muted, I'll just assume I'm hearing a chorus of what I expect. And I expect 4, because this string here, f2.integer, we set it to 4. We better bet that this better be 4 now. So it is. But here's the interesting one. What about f1.integer? We didn't associate these fields here with self at all. So f1.integer, it's probably the same as f2.integer. So by setting f2.integer, maybe we also set f1.integer. Well, it turns out we actually didn't. f1.integer is still 1, which is probably not what you expect. These kind of look like static fields. A static method is associated with the class itself, and these fields look like static fields because they look like they're associated with the class itself. But it turns out that by assigning to f2.integer, we overwrite f2.integer, but not f1.integer. So what's going on here? Oh, I just got a little more chat. Oh, there's a chat. Oh, all right, I found the chat. But aren't F1 and F2 different instances of the same class? Yeah, F1 and F2 are different instances of the same class, which is why we thought that maybe F1.integer would be 4, because we thought that this dot integer thing belonged to the class, and accessing it through the instance was really referring back to this original thing. But that's not what's going on. So we'll dig deeper. Did that answer your question? I'm not sure. I don't know who you are on the.
Yeah, I did.
All right. Yeah, we'll dig deeper, and we'll see some more weird stuff that might explain. So if we look at the f2.dict now, it actually contains integer, and it maps to 4. So that's interesting. We saw integer mapping to 1 in the classes.dunderdict, but in the instances.dunderdict, we get integer also, but the new integer. So now what if we look at f1.dunderdict? I know there's a way to do a poll in this, so maybe I could, but that's not worth it. To me, there's 2 different things that this could be. It could be integer mapping to 1, or it could be empty. Why is the classes.dunderdict a mapping proxy and not a dictionary? Because, so I said that this class body kind of looks like a dictionary, but it turns out that class construction Python actually wraps it up in a different thing. It's technically a read-only dictionary, so if you try to modify that dictionary directly, you can't do it. So that's why it's a mapping proxy. It's how class construction works. Yeah. Good question. But that's just the class.dunderdict. The instance.dunderdict is just a regular old dictionary, which means you can modify it, which we'll actually take advantage of later. So this f1.dunderdict, it turns out it's empty. But that's a little weird. We were able to access .integer on an f1 right here. So how are we able to access f1.integer if f1.dunderdict is empty? Well, we'll see. It turns out that there's a hierarchy of lookups. So if Python can't find the attribute that you're looking for in one .dunderdict, it'll fall back to more and more general .dunderdicts. So by looking up f1.integer, we didn't find it in f1.dunderdict, but we did find it in foo's.dunderdict. Questions about that?
So when you say f2.integer equals 4, does it overwrite the integer equals 1 at class foo, or generate create a new variable and set that to 4 instead?
Good question. Yeah. So by setting f2.integer to 4 here, we're actually adding a new field to f2's dunderdict. And this f2 will kind of override, similar to inheritance. F2's, the instances dunderdict, overrides the classes.dunderdict, but only for that instance. So by setting f2.integer to 4, we're overriding this integer, but only here. So we're creating a new one. Yeah, good question. But when we access f1.integer, we're still accessing the old one. So now there's 2 integers, so to speak.
So then is there a way for F2 to get back to the classes version of it? Or is it been overwritten now?
Is there a way to F2 to get back to the class's definition of it? Yeah, great question. Because unlike inheritance, there is no super here. There's no clear way of getting from your specific instances dunderdict to your classes dunderdict. The way you would have to do it is explicitly to reference your class. So if F2 in some method or something wanted to access the class's original field, it would have to say, capital F foo.dunderdict or capital F foo.integer. The other thing you could do actually is you could delete this. You can say del f2.integer, and that'll delete this attribute. And it will no longer be in the dict, and so it'll fall back to going back to the class again. Yeah, good question. Other questions about this?
If you have like a subclass of foo, does that make the hierarchy taller by 1?
Good question. Yeah, we'll get to that on the next slide. But subclassing does add to the hierarchy, yeah. Yeah. So if we access f1.mylist, we haven't set f1.mylist, so it's not going to be in the dunder dict, so we fall back to the original class, and so we should get the empty list, which we do. But now, let's say we append 10 to f1.mylist. What is f1.mylist now? Well, just like before, I'm going to assume I'm hearing a chorus of the list containing 10. And that's what we get. Yeah, because we appended to this thing. And so we better hope that that thing now has that thing. But f2.mylist, that will still be the empty list because we fall back. Nope. So you have to make a difference between attribute assignment and attribute modification. So here what we did when we set f2.integer to 4 is we did an attribute set. We actually performed an operation called setting the attribute. Here we didn't really set anything. We didn't use an equal sign. We accessed and we called a method. So this access got us the old integer, and then we appended to the old integer. And f2 still also does not have a mylist. So when we access f2's mylist, we still go back to the old mylist. So now every list has 10 in it. And that's because we didn't actually do an attribute set. We did an attribute modification. This is really attribute access. Really what we did here was we accessed the attribute. We didn't do a set. So this kind of like shadowing and hierarchy only gets weird when you're setting things on that specific dict. If we look at f1.dict now, it's still empty. We didn't set it. f2. There we go. Yeah. Shoot. Questions about that? About the difference between setting the attribute and accessing and then modifying the attribute? All right. So now if we call f1.foo of 3, well, earlier here we called foo.foo on 2, because foo here is just a lambda expression that takes an x. So here's x, 2 is x. So this should work the same way, right? Because f1 doesn't have a foo, so we're going to look it up in the class. The class does have a foo, it's this lambda expression, we call it on 3. That's actually not what happens. We get a type error saying that the lambda expression expected 1 argument, but 2 arguments were given. Does anybody know what the extra argument was?
Is it self?
Self, yeah.
Yeah, it's self. And that's because when you're accessing a callable thing, I shouldn't say that. When you're accessing a function on an instance, even if that function isn't even in the instance's dictionary, it gets returned as a method. And methods automatically have self passed in. And later on in these slides, we're going to look at exactly how that happens. But for now, we can just think, oh, okay, yeah, f1.foo, that's a method, so it takes in self, and so that's why there were too many arguments. So now if we call f1.foo on just nothing, that actually works because f1 is x. Now what about this? What are we doing here? We're doing attribute assignment, we're doing attribute set again, but now we're doing it on the class itself. That's totally fine. That is totally doable. So we're setting foo now to a new lambda expression that takes in self and x. And now if we call f1.foo on 3, it works because f1 gets passed in as self and x gets passed in as x. But now if we call foo.foo, we have to pass in both of those things. Just like a regular static method. You know, whenever you access a method statically through the class, then you end up having to pass in self. So this is us having to pass in self. Questions about this slide? All right. So yeah, inheritance. How does this work with inheritance? Well, let's say we have a class bar that inherits from the class that we had before, and we define some subfield. And we make an instance of bar. And then we set b.z to 1. If we look at b.dunderdict, what do we expect? I'll just assume it's a chorus of z out there because we don't expect to see anything defined in any of the classes. The only thing that we've actually set on this instance directly is z. So we get z in this dict. And if we look at bar.dunderdict, similar to the previous slide, we just get the things that are directly defined in that class. So we get subfield. We also get the doc string. Yeah. If we look at foo.dunderdict, it hasn't changed. It is exactly the same as before. Let's look at object.dunderdict, right? Because all classes inherit from object. So if we're talking about doing this kind of lookup chain up the superclasses, then we should also probably look at object.dunderdict. And we see a whole bunch of stuff. We can see the string method, getattr method, setattr, delattr, some less than. These are all the things that are built into every object. So whenever you define the dunder string method, you're really just creating a shadow of objects dunder string attribute. And so the way these lookups happen is when you access something on an instance, it checks up the hierarchy of dicts. It first checks the instances dicts, then the classes dict, and then up the MRO of that class. So that's kind of a pain, right? Now, if we wanted to know like what we can access on a given instance, we have to like loop through the MRO, and nobody wants to do that. That's why this function dir is actually pretty cool. We briefly talked about it in reflection last time. So, but in case you don't remember, the dir method returns as a list of strings, everything that you can access as an attribute off of this instance. And now we know that's actually not so trivial because that's actually walking a hierarchy of dicts. So we see z, subfield, all these things, all objects things. So dir lets us kind of combine these dicts into one thing at runtime. And dir is reflection. So what we're talking about today really deep down is reflection. The whole thing is reflection. And the takeaway here is that attribute access goes instance dict, class dict, and then the MRO's dicts. And when you set an attribute, it always sets on the instance itself every time. So questions about that? Khan says nice in the chat. Or should I not have said that? Is the chat anonymous to you guys? Can you see the... No, it's not. Okay, so you guys know who's sending these messages already. I didn't want to be accidentally revealing people's anonymous messages. Doxed. All right. Okay, any questions about this? We now kind of know how attributes are looked up on dictionaries. These dictionaries kind of represent class bodies or instance collections. Now that we know about that, how are we going to actually manipulate those dicts, right? Because this is metaprogramming, and half the battle is modifying the code structure. Like we want to, metaprogramming is treating data as code, or sorry, no, treating code as data. Whew. Metaprogramming is treating code as data, and part of treating things as data is being able to change that data, right? So we want to be able to manipulate these attributes, but now we just learned that there's this whole hierarchy of them, and that's a hassle. So it turns out Python gives us some functions that lets us do that much easier. We have hasattr, getattr, and setattr. And the way these work is you pass in something, anything, and you can check if it has that attribute. And it'll look all the way up the hierarchy. you can get the attribute. You can set the attribute, and then these apply to the dicts like how you would expect. The cool thing here is that we're accessing these attributes with function calls and strings. So we're clearly seeing here that what we think of as program structure, the attributes that objects have, we think of that as structure. We think of that as kind of defined. But because it's all represented as a data structure, a hash map, a dictionary, we can manipulate that structure at runtime with these methods, with strings, with other data. So that's pretty cool. So similarly, there are dunder methods for modifying how classes manipulate that stuff. So let's look at a dunder method. We're going to make a class called get or infiniteattr, and it's going to define this method, getattr, dunder getattr, and it just takes in a name and self. And getattr is the fallback if an attribute is not found normally on this instance. So what we're saying here is, if we weren't able to find a name attribute on this object, then go ahead and set attr on myself to that name and make the value of this attribute an instance of infiniteattr. So this is recursion, kind of. This is this is a recursive data structure now, because this self instance of infiniteattr is going to have references to other infiniteattrs. So this is a recursive data structure. I lost my mouse. And then we're going to return whatever that thing was. We're going to get that attribute. So now if we make a foo, we can access any attribute on this thing, because any kind of failure of attribute lookup is going to result in this code being run. And we're going to go ahead and just set that attribute. So foo.a is now defined, even though we never wrote a self.a, we never put a anywhere. We can do this over and over and over again. You can do it programmatically thanks to the help of getattr. So like if we just getattr on foo over and over and over again, that'll work. And it'll always just generate a new infiniteattr to represent this chain of attributes. Another interesting thing here is that usually you'll get a Python syntax error if you try to say like foo.1, like foo dot the number 1, because that doesn't compile. Attributes have to have names that start with letters. But that's only a Python syntax thing. It turns out underlying attributes can be anything. And so here we're looking up attributes that start with numbers. This I variable is a number. So we're looking up attributes that start with numbers that wouldn't usually compile. So you can do all sorts of weird stuff with this. And this might look totally useless, but it actually turns out that mock, the class mock, does something very similar to this. Mock is used for unit testing to be able to represent mocked objects. So the mock object, you can pass in a thing and it will return a new object that looks like that thing but actually isn't and has no side effects. So if you're curious, you can look up how mock works, and it actually does similar kind of get attribute hacking. Questions about getattr?
I had a question actually. It's Wyatt, by the way. So you can set up at runtime a class which has an attribute of a number, like, well, yeah, a number. But at compilation time, you can't set up, foo.1. Could you use eval or something like that to compile it at runtime?
I don't think so, because eval is going to also parse that Python string that you pass in.
Okay.
And it's really a string parsing issue. It's not, there's no reason why you can't have an attribute that starts with a number, except that just makes an ambiguous parsing situation.
Right.
Yeah. So if you're representing it as the Python code as a string, probably not. But if you're representing it programmatically through these method calls, then you can do anything you want. Yeah. You could even have an attribute that is the empty string. How would you even type that out? You would just type dot and then put nothing after it? How does that work? That definitely would not parse, but you could do it with these functions. Other questions? All right. So we've got a lot of tools now. Let's try doing something useful with them. Let's make a class that's immutable, right? That's generally a pretty handy pattern in programming. Is when you make something immutable, then you don't have to worry about that data changing on you. You know, for forever and always, that data will be the same. You can look it up once. All sorts of benefits to having immutability. So let's try it. Let's make a class immutable, and it takes in an x and assigns that x. And then we're going to override the setattr function. And as the name implies, this overrides what happens when you try to set an attribute on this thing. And we're just going to say attribute error. You can't set. No setting on this thing. So this seems like a reasonable approach to making an immutable class. And so let's make an instance of it. Does anybody know what's going to happen here? There's a bug in this code. The init method, what does it do?
It tries to set x, but it's not going to be able to.
The init method has one job, and it tries to set an attribute. But then we implemented setattr and said you can't do that. So we get an attribute error. We get our own error every time you try to make an instance of this class. So, okay, this didn't work. So let's take two here. We've got an init method. We're going to set that x because we still have to do that. I mean, there's no getting around that. We're going to have to set something somewhere. But now we're going to check to see if this class has that attribute. And if it does, then we're going to throw the attribute error because we only want to prevent changing the attribute. But it's okay to set it for the first time. So if we already have it, that's a problem. But if we don't, then setattr. Then we actually want to, apply that, that set. Okay, let's give that a shot. Does anybody know what's going to happen here?
I don't think we'll have it by the time we're trying to assign it.
Yeah, that's true. So the hasattr check here will do what we want it to do. When we set this attribute x, x does not exist on self yet. So this is not the problem. Hasattr works as expected. The problem is in that this setattr, what does it do?
Well,
It calls
just call-
dunder setattr.
Yeah.
Yeah, setattr is just going to try to apply this thing to this thing. But that's the function we're overriding. So this is actually an infinite recursion. If you're overriding dunder setattr, you can't call setattr on yourself unless something has changed, unless maybe now setting that attribute will put you in some different, you have to have a base case. This is recursion. So, okay, close. So take 3. Everything's the same. The line got broken a little weirdly here, but everything's the same. But now this time, instead of calling setattr, we're just going to modify the dict directly. Because we already saw, whenever you set an attribute, we always set it to the most specific dict possible, the instance's dict. So that's what we're going to do. We have a reference to the instance, and we have the dunder dict. We're just going to set it. Bing, bang, boom. So now if we make an immutable thing, we access .x, that worked. Yeah, x got set. And now if we try to set a new thing, that works too. But, and if we look at the dict, it's what we expect. But then if we try to change what y is, well, now self has this attribute y, so we get an attribute error. So this is kind of an immutable object. Full disclosure, you can still modify the object through the dunder dict. So this only works assuming that whoever is writing this code actually only uses regular dot notation to do this stuff. And then the other full disclosure is that this is generally discouraged. If you really want an immutable object in Python, the recommended way to do it is to inherit from a built-in immutable data structure. So Python has tuples built in. Tuples are immutable. So the kind of like recommended way to make an immutable thing in Python is to inherit from tuple. But that's actually kind of a pain. And there's all sorts of other cool stuff you can do with setattr. You can restrict certain attributes. You know, this ability to override and then raise attribute errors is actually pretty cool. So questions about this?
Can you go back to the first try?
First slide completely?
First try.
Oh yeah.
First try of this. Would this partially work if we indented setattr inside init? So it would like change after we set self x equals to x?
So you're saying actually implement this function inside of init?
Yeah.
Yeah, that would work. That would work. It's actually kind of annoying. It's hard to do that. Actually, no. No, that wouldn't work. Because you have to consider what thing you would be defining that function on. So defining setattr here, we're defining it in the class body. If you were to define it in init, you would be defining it on the object.
Oh yeah.
And that wouldn't work. You could, in the init function, define it on the class, but then it would be defined for every instance. So you would still run into issues. So no, that wouldn't work. That wouldn't work. Good thought though. Other questions about this immutable implementation? All right, awesome. We are going to get into the crazy stuff now, as if that wasn't crazy. So I said we were going to look at how methods get bound. So let's try writing some methods here. We've got a person, and this is just a fun little hack. Now that we know about dicts, this is a person class that will just make whatever attributes we pass into it. So we're going to collect all the keyword args here and just update the dict with whatever got passed in. So here, if we make a person and we pass in a name and an age, all of a sudden we just implemented person with name and age, but we didn't really. So this is hacky. Don't do this. But I just wanted to demonstrate that it's possible when you know about how the class is actually represented. But we forgot a talk method here. Isn't that our favorite example? We love having a person class and then a .talk method just to make sure that things are working. So let's try adding it after the fact here. We're going to say p.talk is lambda self and then print some stuff. Easy peasy. Now if we call p.talk, this lambda expression just took in self. And we're printing this thing, so we should expect that thing to get printed. We actually get a type error because that lambda expression expected self. Well, wait a sec, that's not what we expect here. We're calling this function on an instance. Shouldn't this get bound up? This has never been a problem before. We've always written these methods to take in self, and self always gets bound somehow. So what's happening here? And just to prove that it'll work, if we pass in p again, it works. So what? Well, okay. Maybe it's because we assigned it to p. P is an instance, so when we did this attribute set, we did it on the instance. Let's try doing it on the class itself, right? Because really that's where we left out. We left off the method definition in the class. So let's just try assigning it to the class. Same exact code, call p.talk. Get the same error. Does anybody know why we get the error this time? That's because this is all just the same code here. We set this attribute on the instance, and so when we look up .talk on that instance, we get that version of talk. So we overrided the class's dunderdict, but we didn't override the instance's dunderdict. So here's an example where we can use del to go back to referencing the classes definition instead. So now if we delete p.talk and we call p.talk now p doesn't have a talk, so we fall back to the person, which now does have a talk. And this works. Now we don't have to pass in self. P automatically gets bound. If we look at p.dunderdict, there's no talk method. We really did delete it. But if we look at person.talk, it's a function. But if we look at p.talk, it's a method. So what's going on here? Like I just said, like, you know, we fall back to the classes dunderdict, but the classes dunderdict implements a function. How did we get here? Basically, we're looking up .talk on the p.dict. We fall back to the type of p.dict. We get that value. The value is a lambda function without a reference to p. And then that function gets turned into a bound method with a reference to p, even though the class itself doesn't have a reference to p. There's obviously some sort of mechanism here going on that we don't understand. And I really tried to figure out a way to demonstrate what that mechanism is, where, you know, some way of discovering it. But honestly, the only way you would ever know how this works is to look it up. And so instead, I'm just quoting Raymond Henniger. The mechanism is in this method, object.dunder get attribute. We looked at getattr. Getattr was the fallback method in case we couldn't find the attribute. Dunder get attribute is the method that we look at before we fall back. So the get attribute method is what implements the falling back. So this is kind of the first line of defense. And it transforms b.x into type of b.dunderdict x, that's what we expect, .dunderget b type of b. So it's not clear what's really going on here, but we now see this new thing, dunderget. We haven't seen that before. So let's try just implementing .dunderget. We've got a class, bindme, and we're going to implement that method, .dunderget. And it takes in an object and type, just like we saw, it transforms it into b and type of b. So that's what we're going to take in. And if you look at the documentation, type is supposed to have a default argument of none. And we're just going to print that that's happening and return some hello string. All right, now we're going to make a class, and we're going to put in it an attribute of bindme. Now if we make an instance of that class, and we look up .x on it, we get our print message. And the value is this string. So what's going on here? What's happening is this attribute value, bindme, has the ability to override how it gets looked up in the class that it belongs to. So this dunderget method does not define how you look up things on instances of bindme. The dunderget method overrides how you look up instances of bindme on other classes. So if bindme is ever included in any other class, its lookup procedure includes this bind print statement, and it always returns hello descriptors. Now if we look up .x on the class itself, we get our print message again, but this time we're binding to none. Before we were binding the bind object to the test object. Now we're binding the bind object to none. That's because this isn't an instance. So we have total control now. Questions about this? This is definitely weird. All right, I'm sure everyone's confused even though there's no questions. So let's see a more practical example here. In Python, you have static methods. There's a built-in decorator for it. And the way it works is if we have a class with a static method, then you can call that method on the instance. Notice we didn't define self here. Self is not part of this, but we can still call it on that C, and we get what we expect, or we can call it on the class, and we get what we expect. Basically, this @static method decorator is making it so that self never gets passed in no matter what. Even if we're calling on an instance, even if we're calling on the class, it basically never passes in self. That's what this decorator does. Well, that's kind of what we're talking about, binding methods and stuff. Let's try to implement the static method decorator. It's just a decorator. We know decorators. So here's our first try. We're going to write a function that takes in a function. We're going to define an inner function. And that inner function is going to take in self because we're wrapping the method, right? We're wrapping the method. And then we're going to call the function, but just without self. Now, if we call our attempt at a static method, it works on the instance, right? Because we define some function that takes in self now, but just refuses to pass it in to the underlying function. This is the underlying function. This is function. This is function. And we're writing a wrapper that takes in self for it and then throws it away. So this worked, but not on the class. The class now has a type error. The class expected, let's see what's going on here. The class expected 3 arguments, 1, 2, 3. Even though self was going to be thrown away, it still expected it. So this decorator didn't work. It turns out we actually need to prevent the function from getting bound as a method in the first place. And we know how that works now. We know it's the get method. So here, we're going to write a class. It has an init method. It's going to take in a function and implement the get method and just return the function unmodified. Now we know a decorator is a function that takes in a function and returns a function. This good static here, this is a class, but aren't classes callable? This class is kind of like a function because we can call it. We call it on a function. And so we can use it as a decorator. So fun fact, you can use classes as decorators because they're kind of like functions that return functions. We wrap this bar method, return A plus B. Now it works. So what do? We overrided the way that this function gets looked up on instances of class with static, such that it always just returns the function. It doesn't do anything fancy. Before we saw the quote from the documentation, the mechanism for binding methods happens in this method. Well, we're overriding this method now in this decorator and making it just always return the function unbound. Questions about that? All right, I had more planned. As you might imagine, there's a dunder set method, which does exactly what you might expect. It changes how you set things. You have to be careful with how you set that because you can, again, end up with recursion. And then we were going to implement a really cool type-checked class where you could instantiate your fields as instances of type-checked. And then the set method on those objects would assert that the value is actually an instance of that type before setting it. So yeah, it's cool stuff. It's very confusing. And if you find yourself wanting to use it, you're probably overthinking your problem because really these methods are really good at creating these kind of environments, these frameworks where you want total control over what people are doing with your classes. So you yourself also really have to know what you're doing. So you see this kind of thing a lot in built-in Python modules, stuff like Django and Flask, frameworks. This is really useful for creating an ecosystem of really tightly checked, very kind of manipulative frameworks that do things on your behalf without you knowing about them. So that's why you don't encounter it very often just by yourself. And it also turns out that it goes very well with meta classes. And we were going to use some exec. So I'll post these slides. And if you're curious, there's all sorts of crazy stuff. And I'll also post a video, a link to a video that really takes this to the extreme. But anyway, I'll go ahead and end this lecture because I'm sure you guys have other lectures to go to. So hope you guys enjoyed. And I'll see you next week for compile time computation. So have a good Corona break.
You too.
Bye.
See you,
Wait.
Max.
I just realized I don't know how to end this.
Oh.
Don't delete the recording.
Oh, all right, I figured it out. All right. All right, see you guys.
See ya.